Okay, section 5.1 is about manipulator Jacobian, including the space Jacobian, body Jacobian, and unit Jacobian. Okay, in this section, we should understand how to derive the space Jacobian and body Jacobian, including the unit Jacobian. Okay, in most cases, the T velocity can be taken to be the six-dimensional twist without loss of generality. In this case, the twist can be described using the Jacobian relationship. Here, it can be decomposed using the column vector, each column vector. Then we have this equation. Okay, here for given the computation of theta of the robot, at that time the six-dimensional vector Ji, each column vector of the Jacobian, implies the twist. It's very important concept in this section. Okay, let's assume that theta 1 dot is chosen as 1. Theta 2, the remaining the angular velocity chosen as a 0 and 0. Everything's a 0. At that time, we can get the twist J1, theta 1 dot. This is assumed to be 1. So at that time, we have J1. Is it right? Maybe you remember the twist has a relation with the square axis and the angular velocity. Let's compare between both. Actually, the Jacobian is a square axis. Each column vector of the Jacobian is a square axis for arbitrary theta. On the other hand, the square axis is obtained from the 0 position. All the computation should be 0. At that time, we can get the square axis. On the other hand, the ith column vector of Jacobian is obtained square axis for arbitrary given theta. Okay, so the square axis of the Jacobian depends on the joint variable. On the other hand, square axis for the board kinematics in chapter 4 are derived for the 0 position. Okay, those are difference between the Jacobian column vector and the square axis. Okay, we have the two standard types of Jacobian. Okay, first one, space. Second one, body Jacobian. Maybe you can estimate how to make the name these kind of things. It is from the space form of POE. It is from the body form of the POE. Anyway, this space Jacobian. Each column vector of space Jacobian corresponds to the square axis expressed in the where? Fixed space coordinate in S. In the case of the body Jacobian, each column vector corresponding to square axis expressed in the end effector frame B. I'm sorry. Okay, let's drive the space Jacobian. Okay, let's begin with the POE of the space form like this. E2 S1 theta 1, E2 S2 theta 2. This kind of exponential map is used to derive for the kinematics of the space form. The end effector computation is given like this. It belongs to SE3. Okay, SE3 has the 4x4 matrix. It is called as the homogeneous matrix. Okay, it has N1 matrix product. Is it right? N plus 1 matrix product. So if we take a time derivative of the T dot, we have the n plus n terms, n product terms appear, because the first term should be differentiated with respect to time t. So this is the first one, and the remaining terms are like this, and then second term should be differentiated, blah blah blah, and then nth term should be differentiated. So we have the 10 terms of POE-like form. Okay. Okay. Here, maybe you know the matrix exponential the differentiation of matrix exponential will bring the same form with the index matrix. So index term, this term going forward, it can be backward, it's okay. There is no difference between both S1 zeta 1 and then the E2 S1 zeta 1 remains. Okay, the other terms are like this. How about the second term? The same principle is applied. So S2 zeta 2 and then the exponential function remains as the same form. And the last term here, okay, Sn zeta n dot and then E2 Sn zeta n. Okay, here in order to derive the matrix form of space twist, T inverse should be multiplied in the latter part. Okay, so it is multiplied to here and here and here. Yeah, then maybe the m and m inverse cancel out each other. This is cancel out each other. So we can cancel everything here. The remaining term will be the S1 and zeta 1 dot. So we have this equation. In the case of the second term, this term is applied to here, m and blah blah. Maybe these terms can be removed, but the last term remains. You right? So this term appears in front side of the zeta 2 dot. Maybe the zeta 3 dot will have this form. Okay, maybe you are good at the orthogonality mapping. It is called as orthogonality map. Is it right? So it can be replaced with the orthogonal this transformation, homogeneous transformation, and S2. Like this, the 4x4 matrix form can be expressed R6. Okay, using the orthogonality map. Orthogonality map implies the coordinate change. So S2, the constant square axis is changed. It has some effect from the orthogonality map of the zeta 1. Okay, the second part, third part is the orthogonality map S1 zeta 1 and E2 S2 zeta 2. Okay. So zeta 1 angle and the zeta 2 angle will have some influence to the zeta S3. Okay. Okay, so it is very complex equation. So let's make it simple. It is the JS1. It is JS2. It is defined as a JS3. So using this relationship between both, we can make the JSI is obtained from the constant square axis by applying the orthogonality mapping from the beginning to the I-1 transformation. Okay, the ith column vector of Jacobian corresponds to the orthogonality mapping of the ith square axis. This is core. let's summarize this property. Okay, it must be the polar kinematics of expressed in using the POE space form. Okay, the space Jacobian is relates the joint joint velocity vector to the space twist. So we have this equation. At that time, each column vector of the JS is obtained from the screw axis by applying the joint mapping. Okay, that's the conclusion of the space Jacobian. Okay, to understand the physical meaning behind the column of the JS. Okay, from here, from the other joint mapping, let's assign this mapping to the T I-1 to denote the homogeneous transformation. Okay, so we can get the adjoint map T I-1 of square axis SI. Okay, to recall that SI is a square axis described the ice joint axis in terms of the fixed frame with the robot in each zero position. Okay, the square axis is obtained from the zero position. On the other hand, each column vector of the Jacobian is obtained from the square axis for arbitrarily given theta 1 through the previous joint angle, theta I-1. Okay. Okay, the adjoint map T I-1 SI is therefore a square axis described in the ice joint axis after it undergoes the rigid body displacement homogeneous transformation. Okay. Okay, we have two example. Okay, here scalar manipulator is shown. Okay, the space coordinate is attached to like this, x-axis, y-axis, and by using the right-hand rule, we can get the g direction. Okay, and the first electric motor is attached to here. The second motor is here. Third motor is here, and both linear motor is attached to the end effector like this. Okay, and then we have the body frame. Okay, here maybe you can get the very easily the square axis. How about S1? S1. The rotational axis is aligned with the g-axis, so 0, 0, 1. The linear velocity, there is no linear velocity, so 0, 0, 2, 0. How about S2? 0, 0, 1, and L1 is remain. Okay, if you consider the rigid body like this, and then if you apply the rotational velocity to here, at that time, this moves like this. You're right? So 0 minus L 0. S3. S3 will be 0, 0, 1, 0 minus L. I'm sorry, that this is L1. L1 minus L2 and 0. How about S4? S4 will be 0, 0, 0, and this axis is aligned with the g-axis 0, 0, 1. Okay, like this we can get the square axis from the zero position. It's very easy. And then maybe the JS1 is obtained S1, and JS2 is obtained adjoint T1 S2. Okay, how about the T1? T1 is very easy because the variable is aligned with the g-axis. So rotation of g-axis theta 1, and there is no linear 1 and 0, 0, 0 and 1. Okay, this will be used to the other joint map. This S2 and other joint map, we can get the JS2. JS3 will be obtained as joint T02 S3. JS4 other joint T03 and S4. If you make your program code, it's very easy to obtain automatically. Okay, now we will consider the physical meaning of the Jacobian. So, okay, after removing everything, then let me talk again. Okay, let's come back to exercise example. Okay, here, as mentioned before, the space Jacobian column vector is obtained from the square axis depending on the arbitrary given zeta1 and zeta2 and zeta3. Previous axis angle will affect the square axis. Is it right? So in here, JS, in order to obtain the JS1, the zeta1 dot should be described in the axis of the z-axis. So WS1 will be the 001. It's reasonable. How about the Q? Q implies the vector from the rotation from the joint to the joint from the joint to the space plane. So this axis is going through the origin, so there is no Q vector here. So we have the zero linear velocity at this point. You're right. It's aligned with the origin of a space plane. Okay, let's consider the second axis, joint axis. It's aligned with the g-axis, so 001. Okay, here it moves like this with the joint angle theta1. At that time, the q vector should be described using the q theta1. Okay, the x will be cosine, y will be the sine, so we have the L1 cosine and L2 sine, and 0. So the v linear velocity is obtained omega cross minus q vector, q2 minus q2 vector. By applying the cross product operation, we can get this equation. On the other hand, omega 3 is aligned with the z-axis, and the q3 is this is the theta 1 and the theta 2. So the end of this point will be described using the cosine two terms. The y-axis with the combination of the two terms of sine. Is it right? Because L1 cosine, L2 cosine theta 1 plus theta 2. The same principle is applied to the here to obtain the endpoint. So this is the Q3. The minus Q3 is required to derive the linear velocity. So the minus Q3 applied to here. Omega 3 is here. And then we have the result of linear velocity. Omega 3, omega 4, this is the linear velocity, so 0, 0, 0, and then this linear velocity is aligned with the z-axis, so 0, 0, 1. Okay, the omega S1 and the JS1 will write down. will be written like this: the JS1, JS2, JS3, JS4. Okay, like this we can obtain the space Jacobian. Okay, here theta 1, theta 2, and theta 3, theta 4, dot, 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 dot. Then we have 6-dimensional twist. Okay, twist here. Okay, it's a little bit much complex example compared to the previous one. Okay, this is the space frame. This is the body frame. Okay. If we want to use the ortho joint mapping, the square axis, it's very easy. S1 and blah blah S6 is obtained, and then you should write down the T01, T02, T03, T06, and then ortho joint map is used to obtain each column vector. JS1 is obtained, ortho joint map. I'm sorry, that it is equal to S1. JS2 is obtained, ortho joint map. I'm sorry. Okay, JS1 is equal to S1. JS2, ortho joint T1 and S2, blah blah blah. JS6 is equal to ortho joint TS5 and S6. Okay, if you know the ortho joint map and the square axis, then you can derive the space Jacobian like this. I think it's easier than the other method, but it does not have any, does not provide any physical insight. So, in this example, we will describe the physical insight. Okay, the first axis is aligned with the G, so 0, 0, 1. Okay, there is some distance between the Q1 and the origin of the space frame as a L1 in the G direction, so 0, 0, L1. Okay, you right? And then if we calculate the VS1 using the cross product, both are G-axis aligned, so we have the 0, 0, 0, 0. Okay, this angle, the theta 2, okay, theta 2 is aligned with the minus x-axis, is right? So minus 1, 0, 0, but the theta 1 angle rotation will, I'm sorry, the Shri weakened. Okay, so the theta 2 rotation, theta 1 rotation will affect the theta 2. So G directional rotation matrix should be multiplied in front side of the minus 1, 0, 0. Is it right? It affects this motion. Okay, so if you calculate this equation, then we have this one. Q2 is the same with the Q1. Okay, and then we can calculate the linear velocity using the cross product. How about the Q3, omega 3? Omega 3 is 0 because the third joint is the linear prismatic joint, so 0, 0, 0. But it is aligned with the y-axis. So 0, 1, 0 will be multiplied the latter part of this equation. And then this linear rotation will be affected by the theta 1 and the theta 2 rotation. So theta 1 and the theta rotation should be multiplied in front side. Okay, so we have this equation. Okay, this has the three axis intersection: theta 4, theta 5, and the theta 6. This kind of joint is called as least center. Okay, this point is denoted by the QW. So QW is obtained from space plane. So 00L1 translation, and then theta 1 and the theta 2 rotation, and then L3 plus theta 3 should be multiplied in the y direction. So L2 plus theta 3 should be added after rotating theta 1 and theta 2. So Q3 is obtained like this form. Okay, I'm sorry, this is the QW. And then the pulse axis is aligned with the Z, so 001. The theta 1 angle rotation, theta 2 angle rotation will affect the rotation axis, so both should be multiplied pronom of the 001. So we have this one. Yes. And then the cross product of omega S3 and the Q minus QW will provide the linear velocity of the S4. Using the similar procedure, we can derive the omega S5 and V5, omega S6 and V6 by collecting the omega and V, omega and V, omega and V. Then we can write down the Jacobian, space Jacobian. Okay. This procedure is very similar with how to obtain the square axis for arbitrary given theta 1 through theta 6. Okay. In the previous lecture, in the chapter 4, a square axis is obtained from the 0 position, not arbitrary given theta. Those are only difference between both. Okay. The body Jacobian is a dual form of a space Jacobian. So I will briefly explain it. Body form of POE is given by like this. Okay, take the time derivative, the first one, blah blah second and third, and the nth derivatives are given, and then T inverse will be applied to the front side, here and here. Okay, then M inverse M, this one, and will be removed each other. Then these terms are remains. Both are remains. That will be corresponding to this equation. Like this, repeatedly applying this procedure. Okay, last one. Okay, the M1, M, both are cancel out, and then the last terms are cancel out. The Bn, theta and dot remain. Like this. Okay, the order compared to the space Jacobian, the sequence is different. Okay, in the case of the mu S is S1 theta 1 dot and E2 S1 theta 1 and S1, I'm sorry, S2 E2 minus S1 theta 1 and theta 2 dot. Okay, the sequence are different, but the forms are very similar each other. Okay, so it is corresponding to the adjoint map of this transformation. So we will use the adjoint map of this transformation of the P1. Okay, and then theta 1 that is applied to here. Like this, using the adjoint map, we can write down the space, the body Jacobian. Okay, as you can see here, the first term in the case of the body Jacobian will be dependent on the theta 2 through theta n. Okay. On the other hand, the last term will be the constant Pn. Okay. Okay, so the later term, not front term, later term will affect the body Jacobian column vector. Okay, so i's column vector of Jacobian, body Jacobian correspond to the adjoint mapping of i's screw joint, BI. Okay. Okay. Definition 5.2 is summarized in the body Jacobian deriving procedure. For given POE of body form, at the time body Jacobian is written by like this. Each column vector of the Jacobian is adjoint map of the BI, the square axis of the body frame. Okay. The last term is the constant square axis. Okay. Okay. The each column vector of the Jacobian is the square axis, square vector of the joint I, expressed in the coordinate of the end vector frame. Okay, body frame, not space frame. Okay. This section shows the visualization, the difference between the space and the body Jacobian. Okay, both are zero position, home position. At that time, we can derive S1, S2, S3, S4, S5. Here, B1, B2, B3, B4, B5. In terms of body frame. Okay, here, if you move the theta 4, at that time this will be like this, right? But the square axis of the S3 does not have any influence from the theta 4 and the theta 5. This axis remains same, right? So the joint variable, including the theta 3, at this time the joint axis is the same. Okay, so joint variable theta 3 and the theta 4 and the theta 5 have no impact on the special twist, right? Resulting from the joint velocity theta 3 dot, because they don't displace axis 3 with respect to space frame. On the other hand, the Q's theta 4 and the theta 5 variation will make the body frame displacement. So this axis P3 should be described in terms of the body frame, new body frame. At the time, the P3 will be changed. The physical is the same, but the coordinate is varied. So P3 description will be changed. Okay. Okay. So on the other hand, the theta 1 and the theta 2 transformation or exponential mapping will change the S3 notation, is right? In viewpoint of S frame. So theta 1 and theta 2 transformation will affect the notation of S3. Okay. As mentioned before, in the case of the space Jacobian, the previous joint angle will affect the description of the each column of space Jacobian. Okay, so S3 should be displaced, should be changed into the JS3 using the adjoint map, using this one. Okay, as mentioned before, in the case of the body Jacobian, the last ended joint angle will affect the description of the square axis. So P4, theta 4 and theta 5 will affect the the P3, is right? So the joint map is used to obtain the JP3 from the P3. Okay. Okay, let's consider a relationship between the space and body Jacobian. As mentioned before, in chapter 3, we have obtained this equation or this equation as a matrix form of a twist in the space in the body frame, space frame and the body frame. Okay, if we wanted to memorize these two equations, in my case, this term is replaced with the PS, and subscript cancellation. We have the SEs remained. At the time, the special twist is obtained. On the other hand, this term can be replaced with the TPS. SEs cancel out each other, then B remains. At that time, body twist is obtained. I like this kind of method to memorize these two equations. Okay. Anyway, we know that the body twist can be expressed, can be changed into the space twist, special twist, using the joint map. The inverse map is also possible. On the other hand, the twist is described using the Jacobian, space Jacobian and the body Jacobian. We have talked about till now. Okay, this equation is a starting point to derive the joint map between the Jacobians. Okay, here we have two equations. Body Jacobian is used to describe the body twist. On the other hand, body twist can be obtained the joint map of the special twist. Is it right? This is used to here. I'm sorry, that this is used to here, and the VS can be expressed using this equation. So this is applied to here, like this, and then zeta dot is attached. Zeta dot is moved to the parenthesis, moved to the last one, like this. Comparing this equation and this equation, we can get the JB can be expressed as a joint map of JS. Okay, so the body Jacobian is obtained from the joint map of the JS. The inverse map is also possible. From here, we should notice that the JB and the JS always have the same rank. If the body Jacobian loses the rank, also, along with the same rule, JS will lose the rank. Okay, because the joint map always have the rank 6, so it does not affect any rank losing. So JS lose rank -1. At that time, JB will lose because both are equality equation. Okay, the last topic is about the analytic Jacobian. It is a little bit different from the space or body Jacobian. Okay, if you many cases we have the many kinds of representation method to of orientation. Okay, such as GYG all angle, GYX all angle, XYG all angle, roll picture angle. There are many representation to describe the orientation. In this textbook, we are focusing on the exponential coordinate. Is it right? So, if you write down the exponential coordinate as a three-dimensional to describe maybe this is the omega hat and zeta. Okay, and then the x, y, e, g belongs to R6. This kind of mapping is possible. Let's denote Q to describe the minimum set of the coordinate. Okay. At the time, end-effector velocity is not given by the twist. The twist is very general form. So in order to obtain the physical meaning of a rotation part of the twist, we will apply the some representation methods as mentioned before, the Euler angle. Okay, so if you write down this notation, this exponential coordinate to describe orientation, it is described as some axis, union axis, and then rotation angle will be applied to here. Like this, we can describe the end-effector orientation. Anyway, the q dot can be expressed using one of the many kinds of orientation. Okay, at that time, we can make some relationship from the joint angle. At that time, this Jacobian is different from the special Jacobian and body Jacobian. So it has another name, analytic Jacobian. Okay, different from the space and body Jacobian body form. Okay, if you wanted to get some more information, you can see, well, you can confirm the appendix B. In here's yes, you can see the GYX and the GYG all angle representation method. As mentioned before, the exponential coordinate is very useful to describe orientation. Maybe the R or omega hat zeta. As you know, the E2R is equal to E2 omega hat zeta will be equal to rotation matrix. Okay. Okay. Text example. Find analytic Jacobian JA with the exponential coordinate to describe orientation. So R is used, omega hat, to describe the axis of orientation, and zeta, the scalar value to quantity of rotation angle. In here, omega hat has the unit magnitude, zeta combined from between the 0 to pi for rotation from the body Jacobian. Okay, if you know the body Jacobian, and if you wanted to write down the Jacobian in terms of the exponential coordinate, at that time we can get the analytic Jacobian. Okay, body Jacobian is here from the body twist. Okay, we know this one. It can be decomposed into the orientation part and the position part, linear translational part. It's very easy. It belongs to R3 3 times n. It belongs to R3 times n. Okay, because twist belongs to R to 6. Zeta dot belongs to R to n. Okay, suppose that our minimal set of the coordinate q belongs to R6 is given by the q Rx. X belongs to R3, including the x and y and the g. As a representative value, x is used in here. Is the position of origin of end-effector plane. R is here. Okay, the coordinate time derivative x dot, x, y, and the g, x hat, y hat, the g hat. The coordinate value of the time derivative of coordinate value is given by the this one, because VB is written in terms of the body plane. It can be changed into the space plane. using the rotation matrix. Okay, so we have this equation. In here's rotation matrix is used already. On the other hand, the time derivative of the R dot implies omega hat and zeta dot. Okay, R dot is related to the body angular velocity. Okay, plus I don't remember this equation. I will skip the derivation of this equation. Anyway, omega b, let's assume that omega b is related to the A matrix from the R dot. If we know the inverse map of the A, we can get this equation. Omega b is described by the omega j omega zeta dot. So we have these two equations. By collecting these two equations, we can make the another Jacobian. It is called as analytic Jacobian. Okay, the A is given by from the R. It is function of the R. This is the homework, one of the homework. In your textbook, exercise 5.10 will require how to derive this equation. So you should submit the derivation procedure of the A matrix in the next in the chapter 5 homework. Okay, by collecting both two equations, R dot is related to the A inverse, X dot is related to the exponential mapping, rotation matrix. So this equation, method multiplication, will be the analytic Jacobian. Okay. Sorry. Okay. The next in the chapter 6, we will deal with the inverse kinematics. From here, we will preview. We will have some preview about the inverse velocity kinematics. So the title is the looking ahead to the inverse kinematics, inverse velocity kinematics using the Jacobian. Okay, the velocity pole kinematics is written by using the Jacobian and the zeta dot. In here, if you attach the S or B, it's okay. S will be the S, B will be the B. So, it is independent of the coordinate equation. Okay. Okay, for given a desired twist is given. Okay, by the usual given twist, the inverse velocity IK inverse kinematics is given by three cases. If J is a square, J belongs to R6 times 6. On the other hand, it has the full length. At that time, we have the J inverse. So, the J inverse applied to both sides, we have zeta dot to achieve desired twist V. Some case J the n is smaller than 6, so actuator is smaller than 6. At that time, the arbitrary twist cannot be achieved. The robot does not have enough active joint, enough electric motor to achieve the desired twist. On the other hand, the number of the motor or number of joint is larger than the 6 at the time. We have the rectangular Jacobian. Okay, Jacobian in this case, Jacobian is very long. Tall Jacobian is pat Jacobian. Okay, tall, pat Jacobian. In the case of the pat Jacobian, we can make the pseudo inverse, not exact inverse. How to make it? It's very easy. J is here, and the J transpose is applied. And so JJT will be the smaller matrix. In many cases, the smaller matrix inverse exists. So if you write down the JJT inverse and then J transpose is applied, it is defined as the Jacobian pseudo inverse. Because if you attach the J here and the J is here, it will be the identity. So this part play a law, inverse matrix law, is right? So it is called as pseudo inverse, not exact inverse. Pseudo inverse is defined as a J transpose JJT inverse to achieve JJ pseudo as an identity matrix. Okay? In this case, Jacobian is very bad. At that time, J pseudo will be given, and then I minus J pseudo J can be added. It's possible because okay, the range space of J pseudo, and then as also in directions, null space of J will exist. At that time, this part will be embedded to here. So J pseudo desired twist is given by in the range space of the J pseudo, and this part is embedded to the null space of the J. By adding this both equation, this will be the J pseudo mu plus I minus J pseudo J, and then arbitrary number will be given. Both are orthogonal each other, so can be added. There is no effect to here. Okay, if you apply the J, okay, let's apply the J both sides. J theta dot J pseudo mu plus J I minus J pseudo J eta. Okay, it will be equal to mu. It is equal to identity, so mu. How about the last term? This is the J. J pseudo J. J pseudo implies the identity, so remaining terms are J. So we have the 0. It must be embedded in the null space. So this term is called as projection matrix to the null space. Okay, like this, the desired twist places a 6 constraint on the joint rate, joint velocity. The remaining 6 freedom correspond to the internal motion of a robot that are evident in the motion of an effector. Okay, let's consider your finger. Your finger has the 3 degrees of freedom, is it right? In the planar, if you make some plane in the motion, okay? At that time, if you fix your end point of the finger, maybe you can make some motion without touching the end effector position. This kind of motion is called as internal motion. Okay, on the other hand, if you okay, let's make the motion following my instruction. Okay, using your hand, grasping your desk. Maybe you can move without touching the end-effector motion. Maybe the elbow can be moved. Is it right? It is called as internal motion. It depends on this term. Okay, without any end-effector motion, we can make internal motion using this term. The human make this one and this motion. Okay, we have talked about the inverse velocity kinematics. Actually, this is the main topic of chapter 6, so later I will explain using the geometry, okay, null space and the range space. Anyway, this is a preview, short preview.